Welcome back to the 31st part of Debugging at Scale, where we debug at cloud scale. Despite the title of this module and video, a lot of the ideas explained here aren't unique to Kubernetes and can apply to all large-scale distributed systems. I have a popular talk on debugging Kubernetes applications. This talk assumes a lot of pre-existing knowledge about Kubernetes basics, which is problematic. I don't want to force too much exposition into a 45-minute talk, but here I can cover some basic introduction and point you at some references you can use to build up from there. If you're familiar with Kubernetes, you might find the terminology I'm using is relatively basic and oversimplistic. The reason for that is that I don't want to explain tooling from the perspective of a DevOps engineer. I don't want to explain everything that is Kubernetes. As I said, most of the talk and articles I see on the subject are very DevOps oriented and assume the type of problems and approaches to solutions. While I think developers should learn DevOps processes, I don't think that should be a requirement. The focus of this module is on the angle of the programmer who wants to be effective in fixing application problems in production without having to learn the tooling, concepts, and processes of DevOps. Notice the term application problems as opposed to configuration file problems, etc. These are problems we would typically face in the actual application source code. First, we need to make sure we're all on the same page regarding Kubernetes, its purpose, and its roots. In the old days, when we wanted to deploy a complex application in production, we had to put a machine somewhere. Developers would either physically set it up or telnet to it. This predates the widespread use of SSH. We'd set everything up and it was all good, until we had to do that again on another site. For that, we built complex installation scripts that would often fail because of dependencies, versions, etc. It also made it very difficult to deal with elaborate settings and manage the resource. Virtualization solved that by creating a virtual machine replicating the x86 OS environment. We could just boot up a fake machine and then set it up in the comfort of our office, then copy the image file to deploy it everywhere. Virtualization let Amazon, Google, Microsoft, etc. sell space on their cloud servers. Thanks to virtualization, we have a guarantee that my app won't collide with one from a different developer. It's amazing, but it still has two drawbacks. The overhead of virtualization is significant. Each virtualization vendor has their own standard. If I built an image using one virtualization server, it might not work on another. Containers solved both problems. They used some kernel capabilities to isolate the current running code. That means it wasn't fully virtualized on the machine, but felt like a separate machine in most ways that matter. To learn more, check out namespaces and cgroups on Linux. A container can run on top of a virtual machine without adding much overhead. The second part was the standardization of a container format by Docker. It gained traction and made it very easy to move container images around. This let developers package an entire application as an image, but it also raised a problem. Say I have an image of my application and it depends on an image of a database. That works perfectly well, but it isn't the end of it. We need a caching server, an authentication server, and we want to scale So we need monitoring, observability, etc. We might move to a microservice architecture where we have many servers. That's the beauty of containers. They make image creation trivial. Because of that, we create many images. Containers enable massive scale. They have very little overhead, but we can further reduce this by creating containers that don't include the full operating system, distroless bare. This sounds like nitpicking in the age of massive storage and RAM, but OS image with everything can have a massive impact when scaled. By reducing this overhead, we can fit more containers on the same hardware and reduce our costs considerably. There are a few things containers don't cover though. Dynamic failover, updates at scale, etc. These, these are solutions that sit above the container runtime. They make sure the service isn't down or overhead and can dynamically provision additional resources. How do we deal with these containers and the dynamic nature of deployment? The solution is orchestration. Kubernetes is an orchestration solution. Container orchestration essentially moves you from host-centric to container-centric infrastructure. It lets you define all the different parts of your deployment, including where you want it to scale, how you want it to scale, etc. The problem is, it isn't magic. For Kubernetes to work properly, everything needs to be set up correctly. Let's imagine I logged into a container and changed its state while we're running. A good example would be adding a configuration option. If this fails and Kubernetes needs to replace the container or scale it up, we might run into serious problems. Before we continue, let's review the stages in history leading us to Kubernetes, which trades between performance on the bottom to hardware neutrality on the top. Let's review the individual stops along the way. Historically, we deployed directly on bare metal hardware. This performed as fast as the hardware would allow. It also scaled reasonably well, but that worked for early web, where the volume of requests wasn't as large as it is today. Virtualization traded performance for portability and easy deployment. This wasn't too bad, but as we did that, the overhead became significant. Containers solved this. They aren't as compatible or portable as virtualization, but they go most of the way and have very low overhead. Practically no overhead at all. They took over the world, and we aren't looking back. And this brings us to Kubernetes. As containers gain traction, a race opened for the leading provisioning solution. Kubernetes came up on top with the most community traction. Since Kubernetes is large and complex with deep history, I've decided to split this introduction to two parts. In the next video, we'll continue the introductory portion. If you have any questions, please use the Slack channel to ask them. Thank you.